My name is Oleg Guba. I am the SRE in the traffic team at Dropbox. And today we'll talk about the Dropbox traffic infrastructure and especially about our edge network, why we decided to build it, how we did it, and how we see its future. Let's start with some numbers. We have millions of users. Those users located in almost every country in the world. We store exabytes of users' data. That's actually an exciting number. And we have corresponding petabytes of corresponding metadata. During the peak time, our infrastructure serves millions requests per second, and we send or receive terabits of traffic. All this traffic currently going through our edge network. We have a lot of points of presence around the world, and our network is constantly growing, and in the near future, we're adding more and more locations. But before going forward, we need to understand why we decided to build this network. We decided to build it to be close to our users, to reduce latency to our users. But why actually want to do it? Let's imagine the situation. We have a data center located somewhere in the United States and user located in Europe. Typical latency in this case would be something like 150 milliseconds. And if we take a look at the TCP conversation, I believe most of us already seen this graph a lot of times. So just a quick round. We'll see TCP handshake, TLS handshake, and actually server request to server and response. Let's say that server has response time 100 milliseconds. Typical latency for the whole request in this case would be 700 milliseconds. It's 7 times more than it's actually needed to process on the server. But let's slightly change the situation. We've added a point of presence close to user, also somewhere in Europe. Server is, data center is still in the United States, user is still in Europe. What's changed? From the client perspective, all the same. TCP handshake, 1 RTT, TLS handshake, 2 RTTs, plus response, request and response to the data center. But in this case, we will have an existing connection from the point of presence to the data center. So we will not pay the high RTT penalty. We will just pay it once. And so by just adding a location close to user without changing any other infrastructure, we can reduce the whole processing time in more than twice. That change will be mostly visible for the interactive traffic, like web browsing, chatting, or something. But you know that all the Dropbox story is about the storing and syncing users' data. So we should be probably focused on the bulk traffic. Here's the graphs of two TCP sessions, one of them talking to the close POP and second one talking to the remote data center. Both of them are using some imaginary congestion control algorithm, which is pretty simple, but it doesn't really matter. On both graphs, we will see two important phases. It's the slow start and the congestion avoidance. And we will see differences in both of them. Slow start phase is actually RTT bounded, so we can expect that it will take way less time. And both, we will see difference in the congestion avoidance phase. We can expect that if packets spend less time in the public internet when going from the user to the point of presence ingress, comparing to going across the ocean, we can expect that it will be less likely to be dropped. Just because less probability of hitting a congestion link, bloated buffer, or something. So all these things will result that by terminating TCP sessions close to user, we can reduce the latency for the interactive reduce latency for the interactive traffic, and we can increase throughput for the bulk traffic. But it's not enough just to add a lot of locations around the world. You need to route users to them. It doesn't matter if you have location close to users, but send his requests somewhere else to the other location. it's not a lot of ways to do it, and so the first of them is BGP Anycast. The second one is the DNS based, when we actually steer based on the DNS server. The third one is URL based approach, when we just generate the explicit link to the needed point of presence. I'll talk about them. So Anycast. In Anycast, configuration is pretty simple. Every single point of presence announces the same IP prefix to the internet. And we have really simple DNS record, static record, which points to one of the IP addresses from that range. And we just rely on the BGP to make all the routing decisions there. That's really good. It works pretty fine. BGP works in the most cases. In the most cases, BGP will choose the closest user location. Also, it has a really great feature like magical failover. In case of one of location goes down, traffic will be fully automatically rerouted to the other locations without any config changes, without anything on your side, which is actually great. But problem with Anycast, that is actually not the latency aware. It tries to optimize number of autonomous systems on the path, tries to optimize number of hops. So we can easily imagine the situation when the routing decision won't be that good. In this example, traffic will be sent for the high latency link just because it has less path on it. And we actually see this difference. Here's the latency measured by our desktop client worldwide. It's comparing the Geo, I'll talk a bit about it later, with the Anycast. We can see that on P50, that's the median, on P75, it's pretty close to each other, but on the higher percentiles, we can see that results are not so good. That's all just because of that misrouting when Anycast makes just the incorrect decision about where to route the user. Excuse me. So, Anycast, simple, fully automatic failover. I forgot to mention, bad thing about not a good thing about Anycast, that you don't have control over the traffic. You can't shift part of the traffic from one location to another. You can't gracefully drain the location. By gracefully, I mean the situation when you need, when you want to switch to that mode operation when no new traffic is coming to the location, but all the existing connections are still being served. So if we don't want, if we, in the Anycast approach, just stop the announcing the IP subnet from the one location, traffic will be automatically rerouted to the other locations. All the existing connections will be forcefully terminated. The second approach is the GeoDNS. In this case, every single location have its own IP subnet, and all the routing decisions are made on the DNS. Usually it uses a precise GeoIP database. It tries to guess the user's location and sends this user to the closest location in terms of distance. That works pretty good. You have all the control over the traffic. You can shift part of the traffic from one location to another. Graceful draining, not a problem with GeoDNS. You can expect that if you stop announcing the POP's IP in the DNS, when TTL expires, there will be no traffic in this location. Sounds really good, but actually doesn't work in this case. Again, here is a graph from one of our locations being drained via DNS. TTL for most of our records is just 60 seconds, 1 minute. But we can see that even after 15 minutes, we have like 10% of traffic there. And more to say, even after an hour, we have 5% of traffic, 5% of new connections coming to this data center. Which means that if we shut down this location after an hour, 5% of our users which were close to this location will notice that something is wrong with Dropbox. And again, GeoDNS is not latency aware. It tries to optimize some metric which is related to latency. And here's an example when it can give you not a best decision. Users are located to the point of presence in another country, close to him, but in actual life, his traffic will take all the way around through lots of different routers, and this routing decision won't be actually the best one. There is a really good way, I really like it, to combine the GeoDNS approach and the Anycast approach. In this case, you, as in the GeoDNS, you announce the different IP subnets from all the locations, but you also announce some supernet containing all the IP networks of all the POPs from all of them. In this case, if everything is up, everything is running, traffic is fully routed by GeoDNS. We have all the benefits of it. But in case of some location is going down, traffic will be automatically rerouted by the BGP for that address while DNS expires, DNS TTL expires. And it will be just kept by other locations. So even if we have stale DNS records for some reasons, users will not notice any problems. So just to summarize it, GeoDNS approach works pretty well. It allows you to make really great routing decisions, way better than Anycast. You have all the control over the traffic. You can shift users from one location to another. Graceful draining is not a problem. As I said, it is not latency aware. It tries to optimize some other metric. Some downside is you need to precise GeoIP database, and you need it fresh, updated, and as it was probably said on the DDoS talk here, you might want to use different GeoIP databases in different regions to improve your quality of your responses. But what if we try to use actually latency as the metric we are trying to optimize? What if we use latency as the signal to make routing decisions? We did it at Dropbox. We added a piece of code into our desktop client, which runs on lots of computers around the world. This client, time to time, wakes up and performs measurements of the latency to all of our locations and sends this data back to us. Here is a really nice picture. This is the visualization of this data. It's actually how internet is visible by our users. The warmer is color, the lower is latency. Actually, if you take a look at this picture, you probably can find the locations of our points of presence. But let's go back to boring slides. No. Using this live latency data and combining it with some additional sources of information, like resolver to IP mapping, because when answering on the DNS server, we don't have exactly the client IP address. We have the IP address of the latest resolver in the chain. So we need to add some logic around here to guess which user is talking to us. Again, some other sources of information, BGP full view, ascent to subnet mapping, definitely data from our monitoring system. We don't want to overload our POPs, we don't want to overload links. Using all this data, we are building actually the latency map of the internet for our clients. And based on this map, we can actually make probably best routing decisions. This is the comparison of this RAM-based approach versus the GeoDNS. We've seen that GeoDNS works not that good at the high percentiles. Excuse me, Anycast approach works worse than the GeoDNS. But here we can see red line is for RAM approach. Red lines are higher, which means, excuse me, blue line is red line is for Geo, blue line is for RAM. We can see that RAM RAM DNS gives us way better results on almost all percentiles, even on lower ones. So almost every user will notice that actually Dropbox works faster. I believe we already discussed that. RAM DNS, it allows you to get the best routing decisions. You have, again, as you use DNS to steer traffic, you have all the control over it. As the downside, you definitely need some infrastructure for that. Actually, some DNS providers already have it and can provide you it, but we've built this part by ourselves. And sure, complicated data processing, if you want to build this map by yourself, you need to do a lot of computation, filtering, aggregation, and all stuff like that. So now we know how traffic goes from the end users to our point of presence. Let's take a deep look inside it. First of all, we designed it to be reliable, simple, and tolerable to the different types of failures. Every our location have multiple connections to the Dropbox data centers using our backbone network. Also, it has multiple connections to the public internet using different transit providers. And also, we have peering connections with our customers. When traffic arrives to the edge router, router uses ECMP to hash traffic to one of the L4 load balancers, and then traffic goes to the L7 load balancer. It looks a bit complicated. Why not something like this? Actually, we can implement this. Also, we can announce the IP subnet from the Nginx box running some open source BGP daemon to the edge router, and ECMP will probably load balance the connections across all the boxes. That will work. It will work pretty fine, but ECMP is actually pretty similar to the Anycast. And actually, it has all the same set of problems. You don't have control over the traffic. You can't, in the most cases, you can't adjust the weight of some single box if you want to do some load testing, for example, or if you want to drain it. Also, the problem here is when you add or remove any of the L7 load balancers here, traffic will be shifted across all of them. So some TCP sessions will be broken. To solve all these problems, we've added an intermediate tier of the L7 load balancers. We use IPVS for that. IPVS is a well-known in-kernel load balancer, and it actually locates pretty low in the network stack in the kernel, so it works really, really fast. And it has two interesting things which helps us to solve all the problems brought by ECMP. First of all, it has connection table. Connection table is pretty simple. It's just in-memory map of hash of 5 tuple of the incoming connection to the one of the chosen backends, and to the exactly one backend. And if there is no record in the connection table for new TCP session, just when new client tries to establish a connection with us, it uses consistent hashing, which gives the same result for the same incoming 5 tuple. Sounds a bit complicated, but let's see how it works. It's actually pretty simple. If you have multiple connections to the our point of presence, ECMP on the edge router will probably load balance them across different L7 boxes, and they will choose some L7 load balancer for that, and their TCP session will be terminated there. If some of the IPVS boxes is going down for some reasons, either maintenance or hardware problems, whatever, then ECMP will notice this change, and it will hash traffic to another alive IPVS backend and IPVS load balancer. And because we're using this load balancer, definitely will not have a records in the connection table, but traffic will be consistently hashed on the same Nginx boxes in this case, so user will not notice any disruption in the connections. And let's imagine the other situation. We want to either drain, or we've lost, or we've added a new box to the pool of the L7 load balancers. We are setting its weight to 0 in the IPVS, and actually we're just removing it from the consistent hash. And no new connections will be scheduled on this box. So all the incoming connections will be rescheduled to across all the pool of the boxes there. But all the existing connections will be still found, data for them will be still found in the connection table. And again, users will not notice any disruption in their traffic. We will just need to wait some time if we drain this box to serve all the connections. Finally, a bit about Nginx. Yes, we use it as the L7 load balancer. All the Dropbox traffic go through Nginx. We use Bazel for building Nginx as well as its configs and some additional tools. Bazel gives us repeatable and hermetic builds, which means that we actually know that, actually building from the same revision from the same repository will give us exactly the same result. And as well as we build all of these configs and Nginx together, we are sure that on the real production infrastructure, we run exactly the same pieces of code which we tested in our test environment. So as I added here, we pack all this data to the squashfs image and distribute it via turn to all the Nginx fleet in the Dropbox, and mount this squashfs image in the read-only mode. So we're sure that there will be no manual changes, no overrides, nothing there. But we still need some dynamic here. As we use Nginx as a load balancer, we need to manage its backend. We need to manage backend's weights. Actually, a couple of ways to do so. First, very simple way is just to generate a part of the Nginx configuration on the target box and reload Nginx. But it will actually lead to the situation when we've lost all the connection to the upstream service, downstream servers, as well actually as to the clients, which actually will lead to the problem I've shown in the beginning of this presentation. We will need to reestablish all the connection to the downstream service. We will need to pay the high RTT penalty multiple times. The second way to implement a dynamic configuration is to use Nginx Plus. It already have all the needed features, and that's probably the simplest way. But at Dropbox, we already have a lot of Lua infrastructure around the Nginx, so we decided to go this way. We implemented actually a control plane for the Nginx. This control plane knows everything about our infrastructure. It knows everything about our topology. It knows where every instance of the application run in the data center. It can combine all this information and provide this information to the Nginx. We have piece of code running in the Nginx, and which in background updates the actually it updates the backends for the given upstreams. This infrastructure it allows us to solve all the problems with the connection reuse, with the dynamic configuration. Actually, it works pretty good. At this point, we also almost discussed everything what I wanted to discuss. So we discussed why we decided to build our edge network, how we did it. Now we understand why latency matters and how we are going to solve this problem. We discussed GSLB approaches and the POP architecture, how traffic goes inside the point of presence. Thank you. We have some of pieces of this architecture is already done, but some of them is ongoing. For example, we have part of the RAM-based routing is done, and I believe traffic team will be focused next year on just improving it and making it fully production ready. IPVS is fully deployed in our infrastructure, but even it's in kernel, even it's really fast, it has its limitations. And when we will be closer to it, I believe now we serve. When we will be closer to these limits, I believe that will be something like 100 gigabits on the single box. We will be thinking of migrating to the XDP load balancers. So there are lots of things to do there. Actually, yeah, that's why I was told it. If you want to join us, you can talk to any of our team, and you can find us in the in the green T-shirts right here. Yeah, thank you. Sure.
Can you talk a little bit about the IPVS, your setup, and what are you seeing as the challenges in terms of scaling that layer itself and managing it?
Actually, IPVS allows us to implement almost like adding the IPVS tier allows us to horizontally scale this architecture and without almost any limits. Probably the first limit we will hit is the ECMP limitations on the networking hardware. Yeah, but by this time we are okay with it.
And what kind of boxes are these? Physically, what kind of boxes, configuration are these boxes?
Actually, the great thing again about IPVS is that it doesn't have any special requirements to the hardware. So all the boxes inside our point of presence, both IPVS and Nginx, are completely the same. This is a typical compute hardware without any like.
So if you have 10 gig here, you're also same boxes are there on the other side. So I was expecting it to be a higher amount of NIC traffic on the IPVS than on the Nginx. But you're saying it's the same.
Yeah, it's completely the same. It's just for simplicity of the architecture inside. But yeah, sure. As you said, it has both of these types of load balancers has different limitations. IPVS will be probably limited in the network capacity and in CPU in some cases on the high packet rates. L7 is probably if you have lots of TLS connections, if you do a lot of encoding there, it'll be CPU bounded. So yeah.
One other thing, are you using jumbo rates in any of these?
No, we don't use jumbos. Yeah. Yeah, sure.
Can you please go to the slide where, in the beginning, where you show the latency issues with the box in the middle?
Sure. It's not the issues. It's just how.
Does this mean that you don't use TCP from the brown box to the blue box, or does this mean that you use an open connection pool of some sort?
Yeah, sure. Yeah, I said probably that we have the connection pool from the point of presence to the data centers. So we just don't need to reopen the connection for every single incoming request.
So that way you're cutting out the 3 layers.
Right. And we actually, yeah, I'm monitoring this connection use pretty tightly, and we are focused on not dropping it for any reasons. Yes?
For the run measurements that you're doing, can you talk a little bit about the frequency in which you have to do those measurements to capture what the current state of the internet is? How dynamic the connectivity is between the different alternatives and how often you have to measure to capture it?
That's actually a really good question. We are working on this part of this project, and currently I believe it's something like every single client measures once or twice a day, so not that often. And it gives a really good coverage. But But for example, if some of the transatlantic links is going down, you might want to reroute this traffic as soon as possible. For this, of course, we will need to implement a different way to measure latency to get this as quick as possible. Again, we can implement some kind of bit more complicated algorithm which will like prefer the more fresh data than the old one, just to start draining the like bad connection quicker.
So the run measurement is happening on the client side or the server side?
Currently, it happens on the client side.
On the client side?
Yeah. Any? Yeah.
All right, one more, different question.
Sure.
For the DNS use case, when you're using the DNS-based scheme, do you have a sense of how much? Do you have a sense of like how much better that would be if more resolvers implemented the client subnet option? That is, you're getting.
Yeah, I believe it will be way better. We compared the data based on the our data against the tests from the resolvers, which provides the EDNS client subnet. And the difference is not that significant, but unfortunately, I believe it's 10 or 20% of traffic now has EDNS client subnet. And also, no, yeah. Sure.
Do you have a threshold in terms of when you decide where the POP should be, your basic metrics around deploying POPs? Is there a threshold that you use for doing that?
That's a really good question, and it sure can be as easy as just find the location on the Earth where it gives us like the better performance. We will probably in this case set it somewhere in the middle of Africa, where like not a lot of actually internet users. So we use this data as well as some additional data sources to understand which new location which will give the more benefit in terms of like users coverage, actual users coverage.
Can you use a GeoIP database or something to figure that out?
GeoIP data.
So how do you sort of classify, these users? Just trying to understand your measurement metrics, kind of what's the approach? Is it using the DNS queries that are coming, or is it?
We have different types of sources for this information, so we can aggregate all of them, and based on this information, like understand where we want to build a new point of presence. Yeah. Any other questions? Sure.
Do you have any examples of using URL GSOP?
Yeah, unfortunately, I probably should spend some time on this slide. This approach is pretty similar to the GeoDNS approach. When you just exactly route user to the exact location, and it just need all the same set of information as the DNS. You need to have precise GeoIP database. Either you want to use the RAM-based approach, it's completely the same. And again, it has all the same set of limits, like if that URL, if the service or point of presence serving this exact URL is going down, we want to do something with it. I had a slide where we combine the DNS approach with Anycast, and this setup might solve this problem. For some cases we use it, but most of the traffic is routed via different types of DNS. Yeah, I believe that's it. Thank you.